Io doesn't look like it belongs anywhere near the rest of the solar system's moons. Most large moons are gray, cratered, ancient-looking worlds, frozen relics that have barely changed in billions of years. Io looks like a pizza that's been left in the oven too long, a mottled surface of yellows, oranges, reds, and blacks, constantly shifting and reforming in real time. That's not a coincidence or a trick of the camera. Io is, without question, the most volcanically active body anywhere in the solar system, more active even than Earth. And NASA didn't figure that out through careful long-term prediction. It stumbled onto it almost by accident through a series of missions that kept returning to this small, violent moon and finding something new and stranger every single time. Io itself is nothing new to astronomy. It was discovered all the way back on January 8, 1610 by Galileo Galilei, spotted through one of the earliest telescopes ever pointed at the night sky, making it one of the 4 large Galilean moons of Jupiter that carry his name in tribute. For more than 3.5 centuries afterward, Io was just a distant point of light, one of Jupiter's 4 biggest satellites, studied only through what a telescope could reveal from hundreds of millions of miles away. It wasn't until the 1960s that scientists even began to understand how strongly Jupiter's own powerful gravity was affecting the small moon orbiting so close to it. Real detailed investigation had to wait for actual spacecraft, and the first to get a good look were NASA's twin Pioneer 10 and 11 probes, launched in 1972 and 1973, which became the first spacecraft to study the Jupiter system up close, with Pioneer 11 taking the first detailed measurements of Io itself. But the discovery that changed everything came a few years later, in 1979, when NASA's twin Voyager spacecraft swept through the Jupiter system. Voyager 1 took the first close-up pictures of Io, and hidden inside the navigation data being processed after the encounter was one of the most famous accidental discoveries in the history of planetary science. An engineer on the Voyager imaging team named Linda Morabito was reviewing images meant purely for spacecraft navigation purposes, checking Io's position against background stars, when she noticed something odd sticking out from the edge of the moon's crescent. A faint, umbrella-shaped plume rising up off the surface. What she'd stumbled onto wasn't an imaging artifact or a star in the background. It was a volcanic eruption, caught in the act, the plume from an active volcano blasting material more than 100 miles above Io's surface. It was the first time active volcanism had ever been, directly observed anywhere beyond Earth, and it instantly made Io the only other body in the entire solar system at that point known to host actively erupting magma volcanoes. The confirmation kept coming. Voyager 1 ultimately identified 8 active volcanic plumes erupting simultaneously across Io's surface during its flyby, and when Voyager 2 followed a few months later, it managed to confirm 6 of those same plumes still actively venting material, along with capturing images of eruptions launching debris up to 62 miles into space. Between the 2 spacecraft, Voyager scientists documented 11 active volcanoes total, along with hundreds of additional volcanic calderas scattered across the surface, structures that weren't necessarily erupting at that exact moment but showed clear evidence of past and ongoing volcanic activity. Just as strikingly, Voyager's cameras found essentially no impact craters anywhere on Io, a genuinely bizarre absence for any solid body in the solar system, where billions of years of asteroid and comet impacts typically leave surfaces pockmarked with scars. The explanation turned out to be straightforward once scientists understood what they were looking at. Io's surface was being resurfaced by fresh volcanic material so quickly and so constantly that any impact crater forming there would get buried or paved over again within a geological blink of an eye, meaning the entire visible surface of Io had to be younger than a few million years old, almost impossibly young by planetary standards. Naturally, this raised an obvious question. Io is roughly the same size and density as Earth's own moon, a modest, mid-sized satellite that, by every reasonable expectation, should have cooled down and gone geologically quiet billions of years ago, the same way our own moon did. So where was all that heat and volcanic energy actually coming from? The answer scientists eventually settled on involves something called tidal heating. Io doesn't orbit Jupiter alone. It's locked into a precise gravitational relationship with 2 of its neighboring large moons, Europa and Ganymede, in what's called an orbital resonance, where their orbital periods lock into simple whole number ratios with each other. That resonance means Io's orbit isn't a perfectly smooth circle. Instead, Jupiter's own colossal gravity, combined with the periodic tug from Europa and Ganymede, constantly stretches and squeezes Io's solid body as it moves through its orbit, flexing the moon's interior by roughly 100 meters with every single orbit, an amount of physical deformation that generates enormous friction and heat deep inside the moon, in much the same way that repeatedly bending a paperclip back and forth generates heat at the bend point. Essentially, Io is being kneaded like dough by the combined gravity of Jupiter and its sibling moons, and all that mechanical stress gets converted directly into the internal heat, driving its nonstop volcanism. After Voyager's dramatic first look, Io went largely unexamined for over 15 years, until NASA's Galileo spacecraft arrived in the Jupiter system in 1995 and settled into orbit for what became a roughly 8-year mission studying the planet and its major moons in far greater depth than any prior flyby could manage. Galileo performed multiple close flybys of Io specifically, including especially detailed passes in 1999 and 2000, and it transformed the fairly basic picture Voyager had sketched out into something dramatically more detailed and, in several ways, even stranger. Using its onboard instruments to actually measure temperatures across Io's volcanic hotspots, Galileo found that some of the moon's eruptions were burning, hotter than any volcano currently active on Earth, evidence pointing toward a type of lava composed of silicate material unusually rich in magnesium, a mineral composition scientists associate with an extremely hot, primitive style of volcanism, more reminiscent of what Earth's own volcanoes might have looked like billions of years ago, back when our planet's interior still ran significantly hotter than it does today. Galileo also discovered that Io possesses an iron-rich inner core, detected during a close December 1995 flyby, along with a surprising high-altitude ionosphere, an electrically charged upper layer far above the surface. That same mission uncovered intense plasma interactions swirling in Io's thin atmosphere, tied directly into Io's role inside Jupiter's enormous surrounding magnetic field. It turned out Io isn't just passively orbiting within Jupiter's magnetosphere, it's actively driving huge electrical currents through it, currents strong enough to spark visible lightning within Jupiter's own upper atmosphere. A genuinely strange demonstration of just how tightly Io's volcanic activity is woven into the behavior of the entire Jupiter system around it, not merely happening in isolation on one small moon. Io's volcanoes, it turned out, weren't simply a local curiosity. Researchers later calculated that these eruptions collectively pump out roughly 1 ton of material every single second into the magnetic bubble surrounding Jupiter, material that goes on to shape and drive much of how that enormous magnetosphere actually behaves. One especially memorable Galileo finding came during a close 1999 flyby of a specific volcano called Prometheus, sometimes nicknamed the Old Faithful of Io, because it had been observed actively erupting during every single spacecraft or telescope observation made over the preceding 20 years, dating back to Voyager's original 1979 flyby. Galileo's cameras and infrared instruments photographed a volcanic crater at Prometheus several times larger than Kilauea, one of the most famous active volcanoes on Earth. And scientists noted genuine similarities between the two, both featuring long-lived lava flows extending outward from a central vent, comparable in style and duration to Kilauea's own decades-long eruption on Earth, just playing out on a moon roughly 400 million miles farther from the Sun. By the time Galileo deliberately plunged into Jupiter's crushing atmosphere in September 2003, ending its mission on purpose to avoid any risk of accidentally contaminating the potentially habitable ice-covered ocean scientists had discovered hiding beneath the surface of the neighboring moon Europa, it had already documented that Io's volcanic activity might be roughly 100 times greater than anything happening on Earth today. And Io's story didn't end with Galileo either. NASA's New Horizons spacecraft, on its way toward Pluto, swung past the Jupiter system in early 2007 and captured its own striking images of Io's ongoing volcanic plumes, adding yet another data point to the moon's decades-long observational record. But the most detailed, most current look at Io has come far more recently, from an entirely different NASA mission that wasn't even originally built to study it in the first place. NASA's Juno spacecraft arrived at Jupiter in 2016, primarily designed to study the giant planet itself, its deep atmosphere, its powerful magnetic field, and its interior structure. But as Juno's extended mission continued year after year, its orbital trajectory began carrying it closer and closer to Io on a regular basis. And, starting in 2023, Juno performed the closest flybys of the volcanic moon that any spacecraft had managed since Galileo's own close pass, back in October 2001. In December 2023, and again in February 2024, Juno swept within roughly 930 miles of Io's surface, close enough to capture the first detailed images ever taken of the moon's northern polar regions, terrain that no previous mission had ever photographed in this kind of resolution. Among the standout discoveries from those close passes was a genuinely striking feature nicknamed Steeple Mountain, along with detailed imagery of an enormous lava lake called Loki Patera, stretching roughly 127 miles across, one of the largest known volcanic features anywhere on Io. Juno's instruments picked up multiple islands rising out of the middle of that lava lake, rimmed by molten lava around its edges, and detected specular reflections off portions of the lake's surface, indicating parts of it had cooled into something remarkably smooth, almost glass-like, similar to volcanic obsidian glass that forms on Earth under comparable conditions. Juno's close flybys also finally helped resolve a genuine scientific mystery that had lingered ever since Voyager's original 1979 discovery. Whether Io's relentless volcanism was being fed by one single enormous ocean of molten magma sitting beneath its entire surface, or by many smaller, separate pockets of magma scattered independently throughout its interior. For decades, the global magma ocean idea had been the leading hypothesis, partly because volcanoes seemed to be scattered fairly evenly across the moon in a pattern that seemed to fit a connected, planet-wide reservoir of molten rock. But by using Juno's uniquely close passes to measure precisely how much Io's solid body physically flexes and deforms under Jupiter's gravity, a phenomenon called tidal deformation, scientists were able to calculate that Io's interior behaves far more like a mostly rigid, mostly solid structure than a body sitting on top of one continuous global ocean of magma. A genuine global magma ocean would have produced a much larger, more pronounced tidal flexing signature than what Juno's instruments actually detected. Instead, the evidence pointed toward each individual volcano being powered by its own separate localized chamber of hot, roiling magma, distinct pockets scattered throughout Io's interior, rather than one giant connected reservoir feeding everything at once, a finding announced in December 2024 that effectively settled a question scientists had been debating for 45 years. That same round of research turned up another genuine puzzle sitting right alongside the one it had just solved. When scientists compared where Io's volcanoes actually sit on the surface against where their own models predicted the moon's interior heating should be concentrated based on exactly how the tidal flexing forces are distributed throughout Io's body, the two didn't line up. The real volcanoes were significantly displaced from the locations those models expected, a genuine mismatch between where the physics says the heat should be concentrating and where the eruptions are actually happening. It's one more sign that, despite everything 4 separate NASA missions have now revealed about this small, furious moon, over a genuinely astonishing span of more than 45 years, from Voyager's accidental 1979 discovery all the way through Juno's ongoing 21st century flybys, scientists still don't have a complete, fully working model of exactly how Io's interior operates. Juno's investigation of Io hasn't slowed down either. In a December 2024 flyby, the spacecraft's infrared instrument, contributed by the Italian Space Agency and known as GIRAM, detected an event of such extreme infrared radiance in Io's southern hemisphere that it actually saturated the instrument's detector. Entirely evidence of a massive volcanic hotspot larger than Earth's own Lake Superior, releasing eruption energy roughly 6 times greater than the combined output of every power plant currently operating on Earth. Scientists on the Juno team believe what they detected wasn't actually a single monstrous eruption, but several closely spaced volcanic hotspots all flaring up simultaneously, suggestive of an enormous interconnected subsurface magma chamber system feeding. Multiple eruption sites at once, a discovery that continues adding fresh, genuinely startling detail to a moon that, more than 4.5 decades after Voyager's first accidental glimpse of an eruption plume, is still actively surprising the scientists studying it. It's also worth putting Io's surface composition itself into perspective, because the coloring that gives the moon its famous pizza-like appearance isn't random either. Much of Io's surface consists largely of sulfur and frozen sulfur dioxide deposited across the moon by its own volcanic activity, which explains the striking palette of reds, yellows, oranges, whites, and blacks that spacecraft cameras have photographed ever since Voyager's first flyby. Despite all that heat pouring out of its volcanoes, Io's actual surface temperature away from active eruption sites runs bitterly cold, dropping to around minus 130 degrees Celsius, since the moon has only the thinnest wisp of an atmosphere and sits roughly 5 times farther from the sun than Earth does. That combination of frozen, sulfur-coated crust, punctuated by localized eruptions burning hotter than anything on Earth, is part of what gives Io its uniquely alien character among the solid worlds of the solar system. The terrain itself is mostly flat plains, rising no more than about 1 kilometer in most places, but scattered among those plains are genuinely enormous mountain ranges, some towering as high as 9 kilometers, taller than Mount Everest, formed not by volcanic activity directly, but by the same intense tidal stresses squeezing and buckling the moon's crust, a landscape shaped by forces almost entirely different from whatever built the mountain ranges found on Earth or Mars. Taken together, everything NASA has found on Io adds up to a moon that behaves almost nothing like anywhere else humans have ever sent a spacecraft. A world roughly the same size as Earth's own moon, transformed by the relentless gravitational tug-of-war between Jupiter and its neighboring moons into the single most volcanically active body anywhere in the solar system. home to hundreds of active volcanoes, lava lakes stretching well over 100 miles across, eruptions burning hotter than anything currently found on Earth, and a surface so constantly repaved by fresh volcanic material that it carries essentially no impact craters at all, unheard of anywhere else among the solid worlds of the solar system. A moon whose furious volcanic output doesn't stay contained to its own surface either, pumping roughly a ton of material every second directly into Jupiter's surrounding magnetic environment, actively, shaping and powering one of the largest, most complex magnetic systems anywhere among the planets. And even after 4 separate spacecraft and more than 45 years of direct observation, still a world that keeps handing scientists new mysteries almost as fast as it resolves the old ones, its volcanoes stubbornly refusing to sit exactly where the physics says they should. Evidence that, despite everything learned, since Linda Morabito first spotted that strange plume rising off the edge of Ios. Crescent back in 1979, the small, furious moon still hasn't finished revealing everything it's hiding beneath that constantly churning pizza-colored surface. There's a particular irony worth sitting with in how Io was actually discovered to be volcanic in the first place. Nobody on the Voyager imaging team went looking for volcanoes that day. Linda Morabito was doing routine navigation work, checking a spacecraft's position against background stars in an image nobody expected to be scientifically remarkable, working late and running on very little sleep after most of her colleagues had already left to return home once Voyager's main encounter with Jupiter was considered finished. It's a reminder that some of the most consequential discoveries in planetary science haven't come from a mission's primary objective at all, but from someone paying close enough attention to notice that something in a routine data set simply didn't look right. The same pattern has essentially repeated itself twice more since. Galileo wasn't sent to Jupiter specifically to study Io's core or its role in sparking lightning in Jupiter's atmosphere. Those findings emerged as part of a broader, years-long orbital survey of the whole Jovian system. And Juno wasn't designed as an Io mission at all. It was built to study Jupiter's deep atmosphere and interior, with Io flybys added on as its extended mission trajectory. Happened to carry it closer and closer to the volcanic moon almost as an afterthought. 4 decades of Io's strangest secrets, in other words, have come less from missions purpose-built to study it, and more from spacecraft sent to explore its neighborhood that simply couldn't resist a closer look once they got there.